Marko Medenjak from Ljubljana. He will tell us about the transport in discrete space-time models.
So first of all, I would like to thank the organizers for organizing this really nice conference. I'll talk about the transport in discrete space-time models. I'll mostly focus on classical cellular automata. However, I'll speculate about possible generalizations and basically where this setup and the conclusions we have been able to reach can lead us in the future. So I'll consider two cases of cellular automata and try to completely solve them, so provide a complete solution of the dynamics of local observables. The first model I'll consider is the hardcore interacting gas. And the second model I'll consider is a reversible cellular automaton 54, where this 54 stands for Wolfram Rule 54. But you'll see later on how the models are actually defined. Okay, I'll start by defining the models, providing tMPA solution, which is a time-dependent matrix product ansatz, and I'll explain what this means. And finally, I'll consider some physically interesting setups and provide analytical and rigorous results, for instance, for transport coefficients in these models, or considering these interesting time-dependent problems like initial inhomogeneous states or quenches. So why would one be interested in studying these models and well, posing these questions? The first reason is basically that we want to find the simplest models, simplest but interacting models, which exhibit certain types of phenomena. And we hope that by basically solving them completely, we can understand what the microscopic mechanisms leading to this macroscopical behavior, which is basically the same as in some more complicated models, is. So we are trying to basically understand out of equilibrium properties. The second question that we would like to address in future is if there are some quantum phenomena or quantum if quantum mechanics shows up on this large hydrodynamical scale. So it would be really nice to see that even if you have very large systems, there are still some observables or fluctuations of some observables which you can measure and on large scales and then say, okay, this is really quantum and not classical. But to do this, we would need to kind of quantize our approach to also understand quantum models. The second point is that we also don't understand basically why we are able to solve these models with this tMPA, basically obtain the complete time evolution of all local observables. So what's the structure behind it? It's not clear how this is connected to integrability of the models, if it is. And this could also enable us basically to generalize these methods to more complicated models. Okay, so enough with the introduction. Let me move to the concrete model. So this model is described on discrete space-time lattice. Time flows up. This is an x-coordinate. And basically, each lattice site can be occupied by three types of particles, if you want. It can be occupied by positively charged particle, negatively charged particle, or it can be vacant, empty. and you do the time evolution in a following manner. So first of all, you take first two sites and propagate them. And if both of the sites are occupied by particles, particles do not move. So if this is positive, this will be positive. If this is negative, this will be negative. But if we have a particle on this side, let's say, and an empty space, or this site being vacant, this particle will move to the first site. And then you apply this kind of evolution to first two lattice sites, third and fourth lattice site, and so on. In the next time step, you basically shift your evolution by one lattice site, so that you kind of entangle also second and the third lattice site. And despite this simple time evolution, you can see that starting from some random initial state, the dynamics looks rather non-trivial. But you can also envision these dynamics in a different manner. So basically you can say, okay, I have some initial distribution of charges, and basically the dynamics is induced by freely propagating vacancies, moving with some constant velocity. And basically these vacancies are just shifting my charges around. Okay, I have said many times that this is very simple, but the physics of the model is rather non-trivial. There are three transport regimes. First of all, if there's an imbalance of charge, so if you take your chain, you put different density of positive and negative charges on your chain, the transport is ballistic, so the transport is ideal. If the imbalance of charge is zero, so the density of positive and negative charges is the same, you get diffusion. This is quite interesting, because you have completely deterministic dynamics. You have just bolts which are scattering elastically, but still you get diffusion if density of particles is the same. And finally, you get insulating behavior if the density of the particles is 1, because none of the particles can move, of course. Okay? So let me explain what the tMPA solution is. So as I've said, it's a complete explicit time dependence of all local observables. And what we require of this tMPA, we can always write tMPA if you want, but we require that we write it in a fashion that's useful for computation, so that its complexity increases maximally algebraically with time, not exponentially. So for our guess, if we take some local observable, okay, first of all, what's a local observable? Similarly as in a quantum system, you basically take some particular observable at site X and maximum entropy state everywhere else. So if you're considering, for instance, XXZ model, you take sigma Z at site X and tensor product, do a tensor product with identities on all other sites. So basically what you do here is take your charge and put it in the environment of maximum entropy. And since the maximum entropy state is preserved under the time evolution, this implies, the discrete space-time dynamics implies that you have a strict light cone. Because if you have particle at this point, it can only move, for instance, in like 3 time steps, three sides to the right. So we have strict light cone, which means that also like non-trivial string will be restricted to this light cone. But you can immediately see that in principle the number of these states increases exponentially with time, with the size of the light cone. So it's very non-trivial, the fact that your description increases algebraically with time. And if you have an MPA solution for a completely localized observable, you can immediately take this solution, basically multiply them together, use standard MPA methods to construct a solution of this non-ultra local observable. So any local observable, not just an observable situated at a single site, can be obtained from these ultra local observables. And what's important is, once again, that complexity remains polynomial in time. Okay, so basically how do we do it? It's quite simple. You just count solitons. So as I've said, here we have, for instance, positively charged particle, which is moving with some velocity. And for instance, here it encounters an empty space, so it just moves to this side. Here it encounters another particle, so it scatters and so on. And we can quite quickly see that basically the number of the particles on the left side of the central particle should be the same as the number of the particles on the right side of the central particle. Or if the central particle moves in this direction, so let's say that there is this soliton is absent, then there should be one more right moving particle on the right of the central particle. And so basically the way we construct the tMPA is by introducing some auxiliary space which counts the number of the particles on the left side of the central particle, and then basically subtracts the number of the particles on the right side of the central particle. So that's why we have to introduce one infinite dimensional auxiliary space which encodes this counting, but additionally we have to introduce some other auxiliary spaces which basically tell us, okay, let's say that now you encounter the central particle. Is the configuration consistent with the assumption that this is the central particle? So is there the same number of particles on left and right side? And if this is the case, basically we prescribe some coefficient to this configuration. If this is not the case, this MPA is made in such a form that we throw this configuration away. So we prescribe the factor 0 to this configuration. And one other simplification is that these factors are all the same in front of all allowed configuration. The coefficients are all the same, which makes the job of deriving this MPA much simpler, since we just have to decide, like, is this configuration allowed or not? And this is a consequence of deterministic dynamics and the fact that we have maximum entropy states on both sides. Okay, so this is how basically this solution looks like. We should also decide on the boundary vectors. And we are able to compute then interesting physical properties. The first one is the Drude weight and the diffusion constant. And the second one is the solution to the inhomogeneous quench paradigm, which we heard a lot about already. But what's interesting in this system is that there seems to be seemingly a contradiction between linear response and the inhomogeneous quench setup. Namely, if we have imbalance of charge, the linear response tells us that we have ballistic transport of charge. But if we introduce the imbalance of charge, like in this inhomogeneous matter, so put some density of charges on the left and some other density of charges on the right, even if we have on average imbalance, we get completely diffusive transport. And this was kind of puzzling at first, but later on we were able to understand why this happens. And the reason is that if you consider like a linear response derivation of Drude weight, let's say, explicitly. So how do you do it? You introduce some gradient of the field in your system, then basically you send your gradient of the field to 0, and then you look how the flux increases in your system with time. This basically tells you the value of the Drude weight. And we have seen that this quench, so linear field quench, introduces also the imbalance of vacancies and flow of vacancies. And as I've told you before, vacancies are the kind of the quantities which propagate completely ballistically, and furthermore, they are the only quantities which propagate completely ballistically, which means that if there's an imbalance of charge, they'll just push this charge in the other direction and introduce ballistic transport of charge degrees of freedom. But this situation doesn't induce any imbalance of vacancies, so the transport remains diffusive. Okay, so the question was, how can we then get a ballistic transport in this inhomogeneous quench setup? We were able to do it by introducing inhomogeneity in the initial state, so putting different densities of vacancies on even and odd sides. And then what you can see is basically that you get a step function profile moving with some constant velocity, as is expected in ballistic regime if you have only single velocity in your system. And then this step function profile, if you look closer at it, again diffuses. So you get an error function profile on top of this step function profile. So then we were also considering the calculation of dynamical structure factor, which basically tells you if you have initially the particle at the origin of your system, what's the probability that you observe the particle at some other site. And we can see basically that we have that dynamical structure factor consists of two parts. The first one is ballistically propagating peaks, which actually do not disperse at all in this system. And this is the consequence of linear dispersion. But then you have like a central peak, which is broadening diffusively, and also its height is decreasing as 1 over square root of t. Okay, we were also able to treat this inhomogeneous quench initial state using hydrodynamics on ballistic scales, and we were able to obtain correct velocities of this domain wall solution. And we did it simply because it's a simple system, so we generally know what GG is, and we were able to express currents in terms of expectation values of charges, and then obtain this result. Okay, so the second model, I'd say, is much more interesting, because for the first one, you could kind of say, yeah, okay, maybe it's not completely interacting, since in principle, your dynamics is described by freely propagating solitons, and then you just dress them with additional degrees of freedom, which are these positive and negative charges. But this model is really interacting, and it was introduced in the 90s by Bobenko and collaborators, where they considered the classification of possible cellular automata, which you get by prescribing the value of the bottom cell from the value of top 3 cells. So this is up cell, left cell, and right cell. So there are 264 possible combinations of these rules, but there are only 2 combinations which produce the dynamics supporting the solitons. So these are kind of integrable cellular automata. One of the prescriptions describes free propagation, and you get it if you just forget about this term. So this is the interaction term, and the second one is this 54 rule, which is given here, and basically this is the interaction. It's a nonlinearity. These are the rules described by pictures, and we can look at what kind of dynamics these rules induce, and it's shown here. So we start from the top. The initial state is given by this on this saw, and then what we do is basically we take, for instance, these three sides, look at the corresponding rules. So okay, this one is blank, these two are black. So the bottom one should be white. And then we go on. And this one should be white according to this rule and so on. And then we move to the next line and look at the configuration on these three sides. Okay, this is this rule and so on. So what is physically happening if we impose these rules is basically that you have solitons moving freely, but when they meet another soliton, they just get a simple phase shift. It's obviously the simplest non-trivial dynamics of solitons, non-trivial, non-free dynamics of solitons. So this system is obviously interacting. Okay. And here we were also able to construct the tMPA solution. So once again, it was done by counting the number of solitons. But if we look at the dynamics and what's happening, the basic idea is basically that, okay, you track the central soliton. And what we see is that basically this central soliton gets displaced from the edge by the number of left-moving solitons that it encounters on its way. So this one encountered 2, so it got displaced by 2 places. But the situation is not that trivial, since you could imagine that you have also a left-moving soliton which didn't scatter with the central soliton, and basically you should exclude those. You should not take them into account where you are considering the displacement of the central soliton. Okay, this tMPA is a bit more complicated, namely it consists of 2 parts. One corresponds to the solitons which were initially left moving. This is this part. And one part corresponds to the solitons that were initially right moving, which is this part. And once again, you do the counting. So basically you count the number of the left-moving solitons and want to match it with the displacement of the central soliton. But then you have to also take into account exclusion of the left-moving solitons which didn't scatter with the central soliton, which requires introduction of another infinite-dimensional space, and then some other auxiliary degrees of freedom, but which are finite-dimensional. And basically, we obtain this tMPA solution for this. So this is for left movers. For right movers, it's quite similar. And okay, these are just the boundary vectors which impose the restrictions that I described previously. So using this tMPA, we were able to obtain an analytical solution of 2 physically interesting setups once again. First of all, we considered a situation when we take the left side of the system at infinite temperature. So this is maximum entropy state on the left side of the system, and we take a 0 temperature, if you want, on the right side of the system, so there are no solitons on the right side of the system, and then look at the dynamics of this initial profile, which is described by this expression, where m is now basically the diagonal away from the central, from the maximal light cone, if you want. Once again, outside of these maximal light cones, nothing is happening due to the strict light cone structure. Okay, well, this looks rather complicated, but when you look at it on the large space-time scales, you can see that basically the description becomes rather simple. So first of all, on the left-hand side, you once again see a step function profile, which is moving with a constant velocity and is spreading diffusively. So this is once again an error function. And once again, the reason for this step function profile, for instance, if you listen to Jacopo's talk or if you listen to Bruno's talk, you'll see that also on these ballistic time scales you get some non-trivial profiles which are a consequence of the existence of different velocities in your system. But in this case we have a single velocity, so the soliton in an empty chain is moving with one velocity. So, and on the right-hand side, there's also something interesting happening, which is kind of similar to what was observed in generic integrable systems, which is basically that you get some peak at the edge. But in our case, this peak is really localized. So if you look at it on diffusive or ballistic scales, you'll see it just completely localized. Generically, this peak also spreads, but once again, because of the existence of different velocities. And here we can once again understand why this peak occurs. So basically, it corresponds to solitons that were coming from the left side of the chain. So there were no solitons on the right side of the chain. Solitons coming from left side of the chain, which didn't scatter with any other solitons. And you can calculate that for long times, this is basically exponentially decaying distribution, so it's really kind of a free regime. But you have exclusion because two solitons can never occupy neighboring diagonals. So that's why you get this type of an anti-correlated behavior in this system. Okay, so the first regime is a free regime. The second regime, which I already described, we called thermalizing regime. Okay, and this is just a comparison between the exact result for long time, which is this error function, and finite time results. Okay, so let me at this point move to the calculation of dynamical structure factor. We've seen that in previous model we kind of have a independent coexistence of ballistic behavior, so these two ballistically propagating peaks, and additionally this central diffusively spreading peak. In this case, we once again have an explicit expression for finite size as finite times. But basically, in the long time limit, what's happening is the following. Okay, we start, of course, with delta peak here, if you like. So particle initially is localized at the origin, and it basically starts spreading with time. And there are two, once again, ballistically moving peaks. But in this case, they develop this diffusively spreading function on the top. So you can see that they are kind of diffusing, and taking this expression, taking long time limit, you can actually see that this corresponds to Gaussian function, which is spreading as a square root of time and also decreasing with the square root of time. So once again, we were able to demonstrate the existence, the coexistence of ballistic behavior and diffusive behavior. Okay, so let me move to the outlook. So the first question is, okay, as you've seen, all of these calculations were basically done by just counting the solitons if you want. But at least in the first case, it's quite clear that there is some underlying algebraic structures which basically these auxiliary objects satisfy, which enables you the existence of this solution. But it's not clear how this is connected to integrability, to any type of Yang-Baxter integrability. And in the second case, it's even less obvious. So it's believed that there should be some underlying algebraic structure, but it's not clear how to derive it. And furthermore, if we knew what the structure was, then we could understand which models we can solve this way, and we could solve them. The second question, which we would like to answer from the physical point of view, and which didn't receive that much, that much attention, are the fluctuations. In particular, since we have a full-time dynamics of local observable, we kind of expect that we are able to calculate exactly anything that's physically interesting, if you want. So during 2000 to 2010, there was a development of so-called macroscopic fluctuation theory for diffusive systems, which basically explains and gives you momenta of your charges, general momenta of your charges, by deriving some non-equilibrium large deviation functional. So it's kind of in similar spirit as was done in for stationary states, for equilibrium states. But it was not done for ballistic systems, so we think that in this case we will be able to do it. And what's interesting and what comes out of this MFT is that some systems exhibit dynamical phase transitions, which are not these dynamical phase transitions which you often hear about in Loschmidt-Echo, just discontinuity in kind of return probability, which I don't know if it has any physical significance, but these are the phase transition where kind of your non-equilibrium state depends on the fine details of out of equilibrium setup. For instance, if you are considering the inhomogeneous quench, if you introduce some slightly different imbalance of particles, let's say on one side, there could be completely different behavior. And then the third point is the relation between the moments of the charges, which they were also kind of able to derive for these diffusive systems. Okay, recently, a month ago, there was a numerical consideration of the quantum version of this model. Basically, the model they considered is the same. So you take this prescription, you have your strings of states, and you propagate your states with this prescription. In some sense, this is still a classical propagation, but what you consider then are the quantum observables. The space of observables is quantum, so they do not commute. And what they were able to show numerically is that the behavior of an OTOC is basically the same as for chaotic system, and they were able to show that entanglement entropy increases linearly with the size of the system. So we hope that with the methods developed here, we would be able to prove this, prove basically what was observed numerically, and furthermore, maybe even prove generalized thermalization in this model. Okay, this is it. And finally, we hope that we will be able to generalize this approach, at least for some situations, to quantum or probabilistic models, and then consider what are the quantum correlations on hydrodynamical scales. Okay, and finally, we hope that we can find these toy models which would exhibit different types of transport universality classes. So basically we were able to construct models which support ballistic, diffusive. The question is what do you have to do, what type of interactions do you need to have in order to get KPZ type of behavior or some more general type of behavior. So the question is, do there exist any other universality classes? So as you've seen, I mean, I've shown you some results and many more questions. So I hope that there will be still a lot of things happening connected to these simple models, and that we'll be able to understand more physics out of it. So with this, I would like to close. Thank you.
Okay, thank you. Questions? Okay, let me then ask one question. So you mentioned at the end this out-of-time ordered correlator.
Yeah.
So you showed how to compute the structure factor already. So with this time-dependent MPA, can you also compute?
It's not directly. You cannot just directly generalize it. So one would you can treat like diagonal observables, but then OTOC in this model is 0. So you have to consider OTOC of two observables which do not commute. And then you cannot directly generalize this approach to calculating OTOC. But we hope that, well, that we'll still be able to solve it. I mean, so.
Okay. Other questions?
Time evolution increase the complexity of the state now with T square.
Yeah.
Right. But is this indeed related to the AUTOC business? I mean,
What do you mean?
I mean, is that this should be exponential to be to fall in the real class? I mean, if it was a really chaotic model.
Well, I mean,
this complexity is a measure also of the degree of chaos, or no?
well, yeah, but then the question is AUTOC in these systems a measure of a degree of chaos? So, and I think it's not clear, right? So, I mean, the complexity doesn't increase exponentially, that's true. So I would say this system is not chaotic at all, but now, the behavior of AUTOC is the same, but I'm not claiming it's a chaotic system. It's not. You have a lot of conservation loss, but still.
Okay, if no more questions, then let's thank the speaker again.